So find the max or min value, max or min, and inflection points on f of x. Okay, and let's say f of x equals the natural log of x cubed over x squared. Okay, so we have to find the max or the minimum values. We're not graphing these. Recognize it would be useful if you take your time to learn how to graph these. But really what we care about is whether this is a max or a minimum point or an inflection point. Where are those located on our function here? So to start off, the first thing you always want to do is check restrictions. So what are some restrictions on f of x? Well, remember, for a natural log, any type of log, you can't have a negative inside. So that means x cubed has to be greater than 0. You also can't have 0 inside a log. Okay, so that should be a little bit of a review there. So that means x simply has to be greater than 0. Okay, that's an important thing to note, so you're not checking and kind of wasting your time checking values that won't even work in your original function. Now to find my max or my min, I need to look for possibly where the first derivative equals 0 or where the first derivative does not exist. Okay, so those are my critical values. So to find my critical values, I have to find my first derivative. Now notice I can use a log rule here. I can take this 3 and put it on the outside and multiply it by my natural log. So 3 ln of x over x squared. Now I'm going to start deriving this because it's a little bit easier. I'm going to have to apply my quotient rule due to the fact that I have a function dividing a function. So here, the derivative of L of x over g of x will equal L prime x times g of x subtract L of x times the derivative of g of x over g of x squared. So L of x is my numerator, g of x is my denominator. So let's start deriving that. So the derivative of f of x is going to equal the numerator's derivative, which is 3 over 1 over x. Okay, the derivative of ln x is 1 over x. Multiplying my denominator, which is x squared. Subtracting my numerator, ln of x. And then multiplying my denominator's derivative, which in this case will be 2 of x, or 2x. And this is all going to be over the denominator squared. So x squared squared. So let's clean this up a little bit. The first thing we can clean up is our x values. So x squared divided by x, that just simply gives me x. And that looks like about all, well, and then we can even simplify this a little bit further because both terms have an x. So I'm going to factor out an x, okay? So f prime of x, I'm going to take out my x immediately, and that will leave me with 3 minus 6 ln x, so that 6 comes from 2 times 3, over, and now x squared to the power of 2, I'm going to apply my exponent rules, a power to a power, you multiply them, so x to the power of 4. And then from here, you can cancel out an x on the top and the bottom, so I get x cubed. So now I have my first derivative equaling 3 minus 6 ln of x dividing x cubed. Okay. Now, at this point, we can start solving this a little bit. Again, my max or my min points can possibly be at when my first derivative equals 0 or my first derivative does not exist. So let's find those possible points. So first off, these are my crit values. The first derivative equals 0. Let's figure out when that occurs. Remember, that only really happens when your numerator will equal 0, because if your denominator equals 0, it does not exist. So when does 3 minus 6 ln of x equal 0? Well, from here, we can start solving for x. So I'm going to add 6 ln x to both sides. That gives me 3 equals 6 ln x. I'm going to divide 6, which will give me 1 over 2 equaling ln x. And now remember, this has a power to, or the base of e. So I can bring that up and it can become e to the power of 1 over 2 equaling x. So this looks like it's a possible value that can either be a maximum or a minimum. We don't know that quite for sure. We have to show it visually. Okay, so possible, max, or min. Now we have to find any other critical values. Okay, our other critical values can be when the first derivative does not exist. Well, our first derivative won't exist when our denominator equals 0. So in this case, x cubed cannot equal 0, so that means x cannot equal 0. But this is why finding our restrictions is important in the beginning. Remember, we have a restriction here where it says x has to be greater than 0. We have no possibility to ever equal 0. So this we're actually going to ignore. Okay, does not fall into restriction. Okay, now that being said, if it's ever like an asymptote, you do have to include it. Okay, but the main idea is when you set up your table, so let's set my table up here to figure out my intervals of increasing and decreasing. Now I've seen a bit of confusion on how to properly do this. I'm not, and it's really important to understand, I'm not putting 3 as its own term and then this as its own term. This entire thing is its own term. So here will be 3 minus 6 ln x. It's everything that's multiplying and dividing each other that's not kind of grasped or included in with each other with a positive or a negative. Okay, so 3 minus 6 ln x has to be included as one term. And then x cubed here is also affecting the sign of our derivative function. So now this will be whether it's increasing or decreasing. Okay. And now remember, this is why we don't really have to take into account our does not exist, x cannot equal 0. Because if we make x smaller than 0, that makes no sense. It doesn't fall into our restriction at all. Okay, so we're not going to include this. What we're going to say is, well, when x is greater than 0 or smaller than e to the power of 1 over 2. Okay, and then what's happening when x is greater than e to the power of 1 over 2? Now, what kind of test value should we use? Remember, you're probably not going to have a calculator, especially if you guys go into university level courses. So in this case, we want to use a value that's smaller than e 1/2. So I would choose something easy to use in terms of ln. So I'm going to use x equaling e to the power of 1 over 4. 1 over 4 is smaller than 1 over 2. So I know that x is going to be smaller than e to the 1/2. So let's plug that in, 3 minus 6 ln e1 over 4. Now I can easily take this out and it becomes 3 minus 6 over 4 ln e. And remember, ln e equals 1. So this is 1, and that will become 3 minus 3 over 2. And that will give me positive 1.5. So it doesn't really matter what the number is, it matters about the fact that it's positive. So that means this is a positive interval here. Any number greater than 0 in x cubed will be positive, so that means we have an increasing interval. Now what's a number that's greater than e to the 1/2? Well, we could use really any number. I'm going to use e to the power of 100. Okay, so 3 minus 6 natural log e to the power of 100. I'll take out that 100, and now I'm going to get e to the power of 6 times 100. And then remember, ln 1, or e, is just simply 1. So that's 3 minus 600, which is obviously going to be a negative number. Okay, so any number greater than e to the 1 over 2 is now negative. This will be a positive value. Okay, any number we put in here that's positive will spit out a positive number. And then you have positive and negative, which makes it negative, so we are decreasing on this interval. So if we draw our number line here, x at e to the 1 over 2, well, and 0 here, between 0 and e 1/2, or 1 over 2, we are increasing, and then after, we are decreasing. So that means this is a maximum point. So that's how I prove and show my markers or people reading my work that this is why it's a maximum point, and this is why I know it's a maximum point. Okay. Now we just need to figure out exactly where that maximum point is on our original function. So find coordinate point for max value. Well, the way I'm going to do that is I'm going to plug in e to the 1 over 2 into my original function f. So remember, my original function here is 3 ln x over x squared. So this will be 3 ln e to the power of 1/2 over e to the power of 1 over 2 squared. And then from here, I can apply my exponent rules. Here I can multiply these two, and I can take out my 1 over 2, and this will become 3 over 2 ln e over 1 over 2 times 2 gives me e to the 1. The ln of e equals 1. So now I have 3 over 2 e. Okay, so that means I have a maximum point at e to the 1 over 2 and 3 over 2 e. So I'm done that section now. Did that make sense to everybody? Yeah. Now for my inflection point. So my inflection point, I kind of have to do the same idea, but remember, inflection point is due to concavities. Inflection point occurs when you have no concavity. So when your second derivative either does not exist or equals 0. So this point, we are going to have to focus on inflection points. Okay, and now more for my inflection points, I'm going to have to look at f of the first derivative we found to be 3 minus 6 ln of x over x cubed. Inflection points occur when your second derivative either is 0 or does not exist. So now we have to find our second derivative. So recognize we have a quotient law that we're going to have to do. Okay, so we're going to have to find the derivative of our numerator, find the derivative of our denominator, and apply the quotient rule. So the second derivative, the derivative of my numerator, well, the derivative of 3 is 0, and then the derivative of negative 6 ln x will be negative 6 over x. Okay, and that's because, again, the derivative of 3 minus 6 ln x over dx will be negative 6 over x. Okay, and then we multiply by my denominator, x cubed, and now I subtract since it's a quotient rule. And now my numerator will be written down, and it's going to be multiplied by the denominator's derivative. The denominator's derivative will be 3x squared. Okay, so that means I have to multiply by the denominator's derivative, and this will be all over the denominator squared. Now at this point, I can kind of take a few things out and go from there. So focusing right here, well, I can already cancel out my denominator x here and make this squared. And now I have x squared and x squared in both terms, so I can take it out. So this will become x squared multiplied by negative 6. And now I can, I may as well apply my 3 inside here. So minus 9 minus 18 ln of x over, and then remember, a power to a power, you multiply x to the 6. Okay. And then from there we can clean a few things up. I'm going to apply this negative inside, and I will also cancel out my x's here. So x squared gets canceled out, and this becomes x to the power of 4. So my second derivative will now be negative 6. Negative 1 times 9 is negative 9. Negative 1 times negative 18 ln x is positive 18 ln x over x to the power of 4. And then from there, we can combine like terms. So this will be negative 15 plus 18 ln x over x to the power of 4. Okay, so now I found my second derivative. Again, it's always important to keep track of signs, notations, or else it can be a little bit confusing and you can make a pretty easy mistake pretty quickly. Now again, we're trying to find my inflection points. So where my second derivative either equals 0 or does not exist. My second derivative will equal 0 when my numerator equals 0. So what value of x will make my numerator equal 0? And now we can solve for x. So add 15 to both sides. 18 ln of x equals 15. And then divide 18. 15 and 18 both have 3 in common, so we can divide out a 3. That will give me 5 over 6. And remember, this is the base of e here, so I can bring it and become the base of our exponent. So x equals e to the power of 5 over 6. So this is a potential inflection point. So now we have a potential inflection point, e to the power of 5 over 6. We also want to check, is there any point that my second derivative does not exist? Well, that's when your denominator equals 0. So x to the power 4 equals 0. Well, that means x cannot equal 0. Remember, sometimes you will take this into account. This one, not so much, based on the fact that x, from our restriction way back in the beginning, simply says that the x has to be greater than 0. So we're not really worried about what's happening on the left-hand side of 0 because it can't happen on our original function. So now we can draw our table. So my table, remember, I'm splitting into terms that will affect the positive or negative of my second derivative. So negative 15 plus 18 ln of x all acts as a one term there. And then that's dividing x to the power of 4. And now this is concave up or concave down. I'm not going to include x smaller than 0 because you can't have that on our original function. I'm going to have my intervals being 0, x being greater than 0, and smaller than e to the power of 5 over 6 because of our potential here. And then what's happening when x is greater than e to the power of 5 over 6? Now again, choose numbers that can be easy. Something to recognize is this is to the power of 4. Any number that you put in there is going to pop out a positive number. So that makes it easy. Some number that's smaller than e to the power of 5 over 6 would be something like e to the power of, let's do 1 over 6. Something nice and simple. So negative 15 plus 18 ln e to the 1 over 6. And now I can take out that 1 over 6 and get negative 15 plus 18 over 6 ln e. Remember, ln e is simply 1. 18 divided by 6 is 3. So negative 15 plus 3, that gives me a negative value. So now a negative and a positive give me a negative. So this is concave down on that interval. Let's choose some number that's greater than e to the power of 5 over 6. So that's a really easy one. We can just put in e. Okay, negative 15 plus 18 ln of e. Well, the ln of e is simply 1, and I get negative 15 plus 18, and that spits me out a positive number. So now I get a positive and a positive, which gives me a resulting positive. So that gives me concave up interval. So now if I draw out my number line here, I have 0 here, I have e to the power of 5 over 6, and when we are between 0 and e to the power of 5 over 6, we are concave down, and when we are larger than e to the power of 5 over 6, we are concave up. Okay, so this is an inflection point. Recall, we don't care what's happening on this side because our function doesn't exist over here. Okay, so we don't really have to focus on that. Now we've found our spot where our inflection point is in terms of our x-coordinate. Now we just have to find our y-coordinate. So that means we're plugging it into our original function, because remember, we're talking about what our original function looks like. So our original function equation is f of x 3 ln of x over x squared. So let's plug in and figure out where the inflection point is. Inflection point coordinate. So f at e to the power of 5 over 6 equals 3 ln of e to the power of 5 over 6 over x squared, so e to the power of 5 over 6 squared. And now from here, we just apply some log rules and exponent rules. So we can take out our exponent. We can multiply in our exponents. It's in the power to a power. And that will give us 3 times 5 over 6 ln of e, dividing, and this will become e to the power of 5 times 2 divided by 6. And then from there we can simplify and solve. So this is 1. This cancels out and becomes 5 over 2. 2 divided by 6, that gives me 3 in my denominator. So I have 5 over 2 dividing e to the power of 5 over 3. And we can simplify that to be 5 over 2 e to the power of 5 over 3. So that means on our coordinate points, it will be when x is 5 over 6, y is 5 over 2 e to the power of 5 over 3. So just to give you a really good understanding, this is our inflection point. You could stop there in the homework that you've been given, but just to give you an understanding, if we were to draw this graph out, we would have our max point at e to the 1 over 2, and then our y value is 3 over 2e, so somewhere around here. And then our inflection point will be somewhere found over here, e to the power of 5 over 6, and then 5 over 2e to the power of 5 over 3. And if we were to draw this, our function is going to roughly look something like, and then remember, it's still concave down here, and then it goes to concave up. So it's going to look something like that. So we have concave down, and then this is concave up here, and there's your inflection. And then this guy's your max. So that's kind of how you do a more difficult question. Again, in order to actually sketch this, you'd probably have to find your x-intercept and go from there. But that's how you find your inflection points and maximum points.